Okay, for tutorial 3, we're looking at momentum transfer of a flow of a non-Newtonian fluid. So the general MATLAB function for solution of a boundary value problem by shooting method using the Newton's technique. So we apply this function to find the velocity profile of a non-Newtonian fluid that is flowing through a circular tube. Also calculate the volumetric flow rate of the fluid. The viscosity of this fluid can be described by the Carreau model. Okay, so we want to use a function to find the velocity profile, okay, and calculate its volumetric flow rate of the fluid, where mu is the viscosity of the fluid, mu0 is the zero shear rate viscosity, gamma is the shear rate, T1 is the characteristic time, and n is a dimensionless constant. So the momentum balance for this flow, assuming that the tube is very long so that n effects are negligible, results in this equation, where delta P over L is the pressure drop gradient along the pipe, and the shear stress is expressed as this. Okay, so before that, we'll understand how this equation works. Okay. So, all right. Okay. So we were given that d, dr, r, tau, rz is equal to negative delta p over l r. Okay. So we will integrate this equation, in which we get r. The integration of this gives this equals to negative delta p over 2l r squared, right? So r plus 1 and then divide by 2 plus c1. Therefore, we know that tau rz is equal to this. This one can be cancelled off, plus c1 over r. Therefore, we get this equation. Okay, so now we can look into the boundary conditions. So at r equals to 0, okay, so let's say we have this. Okay, and let's say this one is the wall. Okay, so for this one, because we have it is over a tube, so our shear stress profile will look like this instead. Sorry. It will look, okay, so the velocity profile will look like this. Okay, so this one is your velocity profile. And your shear stress profile will look like this. Okay, so you have a higher shear stress near the wall, and the shear stress in the middle where r equals to 0. Okay, this one over here should be 0. Okay, so that is our first boundary condition. At r equals to 0, tau rz equals to 0. Okay, so we substitute the boundary condition into this equation over here. So tau rz, this one is 0, equals to negative 2p over 2, delta p over 2l, r is 0, plus c1 over 0. Therefore, since c1 is over 0, so c1 has to be 0. Therefore, this equation becomes this, like that. So, okay. So we were given that tau rz is equals to negative mu dvz as a function of r to dr. Alright, now, so we substitute this tau over here to solve for our vz. Okay, so negative mu dvz r over dr is equals to negative delta p over 2l r. Right, so dvzr over dr is actually equal to delta p over 2 mu l r. Then we integrate this, okay, integrate vz with respect to dr. We should get okay, so with respect to dr, so this one 1 plus 1 equals 2 divided by 2, so 2 times 2 equals to 4 mu l r squared plus c2. Okay, again we look at the boundary condition for the velocity. So at here the velocity is the highest at r equals to 0, but at r equals to r, so here is at r equals to r, your velocity should be 0. Okay, so that is your second boundary condition. Where r equals to r at vzr equals to 0. Okay, so we substitute the values back into this equation. So over here we get 0 equals to negative p over 4 mu l. This one becomes r squared plus c2. Therefore, c2 is actually equal to negative delta p over 4 mu l r squared. Okay, so then we can write the final equation for this, which is v z r equals to delta p minus capital R squared. Okay, so we can factorize this. Here we can factorize this into delta P over 4 mu L R square minus R square capital. So the maximum velocity is at when R equals to 0, right? Remember? So the maximum velocity is given when R equals to 0 over here. Okay. Oops. Therefore, our maximum velocity is such. Okay, so we know that negative delta P over L is 20. Therefore, in the MATLAB code later on, okay, I'll explain this later, P max at 0 is delta P R square over mu. Okay, so we look back at the question. All right, so this is the pressure drop along the pipeline. Okay, we've done that. So therefore, equation 1 is a second order ordinary differential equation which should be solved with the following boundary condition. Okay, so this is your maximum gradient. Okay, your maximum velocity gradient. So the required data to solve this problem, this one is given. Okay, later we'll have to input these into the solving in the MATLAB. Okay, so first we have to define two dimensionless variable. One is a dimensionless distance and another one is a dimensionless velocity. Okay. So where v star, okay, is equal to this. Okay. So equation 1 can be expanded and rearranged in its dimensionless form into the following second order differential equation here, where lambda equals to T1 V star divided by R. So to obtain the canonical form of equation 2, we apply the following transformation, whereby we set y1 equals to d theta over d eta, and y2 equals to theta over here. Okay, I call this theta. So substitute this in. So we have 1 over n equals to, this one is y1. Simplify it, where y dy d2 over dn is y1. Okay, the change of this variable. So the set of nonlinear ordinary differential equations 3 and 4 should be solved with the following boundary condition. Okay. So the initial value is known, but the initial value of y2 must be guessed. So we designate this guess according to this. Okay, so take note of this. So the value corresponds to the fluid velocity at the center of the pipe if it was a Newtonian fluid viscosity of mu O. So the complete set of equations for the solution of this two-point boundary value problem consists of the four system equation with their known boundary values, equation 3 to 6, the guess initial condition for y2, equation 7, a Jacobian matrix, an equation to calculate the delta y vector, equations to correct the guess initial conditions, and repeat the iterations. So we will use the following MATLAB programs. Okay, I have uploaded the file in your Canvas, so you just have to download it and save it into your MATLAB files. Okay, so we'll look through the MATLAB programs for this example. So this is the input data that we want to put in when we run our MATLAB function later on. So for R is an input, so we set it as inside. Okay, so for the R value, okay, when we calculate, we want to put in the R value, it is the inside diameter of the pipe in meter. Okay, dP, the change in pressure, the pressure drop gradient, the zero shear rate viscosity, okay, the characteristic time, the exponent n from the power law, and the M file containing the set of differential equations. Okay, this one we'll explain later. And the order of the Runge-Kutta method that we want to use, as well as the step size. So Vmax is actually dP times R squared over 4 mu. Right? And then lambda, we have already we were given lambda is T1 multiplied by V star over R. Okay. Then the solution of the set of differential equations. Okay, we will use the shooting method where R equals to eta multiplied by R, capital R. This one is our dimensionless form. Vz is y2 multiplied by V star. Y2 multiplied by V star, right? Okay, so we can see it over here. Y2 multiplied by V star is Vz. Okay, Vmax, sorry, and V star. And Q is the flow rate, which is 2 pi, and with accord to the integration of Vz times R with respect to R. Vz times R with respect to R, Trapp's mean integration. Okay, and F print means the solution will show the flow rate in liter per second, and we will take Q times 1000. Okay, then to plot the results, because the question also wants us to show the velocity profile, so we will plot 1000 times R to Vz. Okay, the x-axis will be your R, your radius, and your y-axis will be your velocity. Okay, then we will see a velocity profile. And your y label, okay, which is your Vz, and this is just a labeling of the name. Then we have your M file containing the what do you call that, set of differential equations. So we are using this set of differential equation, which is equation 3 and equation 4. Okay, so dy1 over dn, okay, these two equation, okay, comes from equation 3 and equation 4. Okay, so then we'll make it into a column vector. So the shooting file is given, as well as the Runge-Kutta method file. Okay, then we'll transfer this problem into the MATLAB and call out the MATLAB program to solve for the volumetric flow rate, as well as for the velocity profile.